In the next section, we are going to discuss glycoside formation. Glycosides are derivatives of sugars in which the cyclic sugar hemiacetal is converted into an acetal by replacing the hydroxyl group on the anomeric carbon with an OR derived from an alcohol. This is the observed reaction. You can see that we start with a cyclic sugar hemiacetal, although this is a simplified drawing because the other hydroxyl groups are not indicated, primarily because many different sugars can do this, and the hydroxyl groups would be different depending on the specific identity of the sugar. You can see that this is a hemiacetal because on this carbon right here, we have connected an O carbon group, oxygen to carbon group, and also another bond to an oxygen hydrogen, in other words, a hydroxyl group. The conditions for the glycoside formation reaction are, first of all, an alcohol, which will become attached to the sugar, and then some form of strong acid catalyst. Many can be used. Probably most common that I've seen is sulfuric acid, but of course we can also use PTSA that we discussed in chapter 18 as an organic strong acid, and we can even use hydrogen chloride gas bubbled through the alcohol to make a solution of the acid. When we form the product at the anomeric center, we typically are going to have two stereoisomers available, one where the oxygen to carbon group that has been added is cis to the tail. We call that the beta, and one where the oxygen to carbon group which has been added is trans to the tail. We call that the alpha stereoisomer. These are both glycosides. They are diastereomers of each other, and we can see that because the anomeric carbon now has two oxygen carbon groups attached, that would be an acetal. We're now going to look at the mechanism for this reaction. Now, this reaction is actually the end part of an acetal formation reaction, which we studied in chapter 18. In chapter 18, we saw that we could start with an aldehyde or ketone. We could treat it with an alcohol and acid. And what would happen is we would replace the double bond to oxygen on the aldehyde or ketone with two single bonds to oxygen, and those oxygens would be connected to carbon groups. When we looked at that mechanism, we introduced our PRAM mechanism terminology. The first three steps, the overall mechanism for acetal formation was protonate, add, make stable, protonate, remove, add, make stable. In other words, the acronym PAM-PRAM. But if we looked carefully at that mechanism, the first PAM, protonate, add, make stable, actually led up to the formation of the hemiacetal. When we work with glycosides, we're going to assume the hemiacetal is already formed. Therefore, all we need to do to go from the hemiacetal to the complete glycoside acetal is PRAM. Protonate, remove, add, make stable. So let's look at that. So if we look, we can see that the initial hemiacetal already has one of the two alcohol ether-like bonds attached. But what we need to do is remove the hydroxyl group to make room for the second acetal ether bond. So what we're going to do is first protonate the hydroxyl group. So the oxygen lone pair reaches out, makes a bond to a hydrogen on our generic base, and we obtain this intermediate, which, by the way, has a typo that I will have to fix later. It's supposed to have a positive formal charge on the oxygen. So that's our protonate step. We're then going to remove this OH2 positive coming off as a water leaving group. That's our remove step, creating a carbocation at the former anomeric center. Now, the carbocation is resonance stabilized by a pair of electrons moving in to make a double bond O in the ring. We will leave this form because this form then has room for us to make a bond from our alcohol oxygen, a lone pair coming in and making a bond to the carbocation. That's our add step, and that forms this intermediate. But this intermediate has a positive charge on the oxygen, which is undesirable. So in a last step, we make stable by deprotonating this positively charged oxygen using a base. Base would come over, remove a hydrogen, pair of electrons would go, and we would, which would result in our acetal, which we call a glycoside because it's formed on a sugar hemiacetal. When we discussed acetals, we also saw that the acetals can be hydrolyzed or treated with aqueous acid, and the alcohol groups removed and converted back into the carbonyl. We can do the same thing with glycosides. If we take a glycoside, we can treat it with aqueous acid, which we'll symbolize as hydronium, H3O+. And the alcohol will be removed, it will be protonated, and then it will be replaced with a hydroxyl group. It should be noted that both in the mechanism and this example, we have not specified the stereochemistry of the hydroxyl group, nor did we specify the stereochemistry of the glycoside. We get a mixture of both stereochemistries in most cases, where some of it has, again, the added alcohol or the added hydroxyl group cis to the tail, which would be beta, and some has it trans to the tail, which would be alpha. Since in many cases, particularly with these cyclic hemiacetals, they open and equilibrate, we often are not going to specify the stereochemistry of the product. We will just use our squiggly bond to the hydroxyl group, indicating that we get a mixture of both stereoisomers. Glycosides can also be named, which can be useful if we're using them as chemical reagents or otherwise. To name a glycoside, we first need to consider that in the structure of the glycoside, we have a sugar piece connected by an oxygen to a carbon group. So what we will do is first name the carbon group of the alcohol that we used to form the glycoside. So for example, here we have this sugar-derived portion, and then here we have an ethyl connected to an alcohol. So we will call this an ethyl glycoside by putting the name of that carbon group in front. Now, we've already talked about how to name the cyclic forms of sugars by inserting into the name either pyran or furan, depending on whether they are 5 or 6 membered rings. We also discussed how the ending of the name of sugars, whether cyclic or open, they end with OSE. So to convert that cyclic hemiacetal name with the ending of -ose into the name of a glycoside, we simply replace the -ose ending with -oside. -ose ending is replaced with -oside. So therefore, if we look at this sugar, which came from beta-D-glucopyranose, we can see that if we replace the OH with the beta stereochemistry using an ethyl alcohol, we would have ethyl beta-D-glucopyran oside. Similarly, for a 5-membered ring sugar like this one, the cyclic form of which comes from ribose, has the beta configuration, therefore it is beta-D-ribofuranose. If we replace that anomeric hydroxyl group with a group derived from methyl alcohol, methanol, we would have a methyl carbon group. We would put that in front. We would still have beta-D-ribofuran, but we would end with oside. So methyl beta-D-ribofuranoside.